Okay, free fall. So, drop a hammer and a feather from the same height on Earth, what happens?
Hammer goes first.
Nope, they're both fall the same.
Really? So, I'll drop a hammer and a feather right now, and the feather and the hammer will hit the ground at the same time.
No.
And
What type of hammer?
It doesn't matter.
No, so
The hammer's gonna hit first.
The hammer hits the ground
Or
first.
it's heavy.
unless you are
No, that's it, right there.
Literally it.
Wait,
What will happen?
in this
Hammer
scenario, yes, the hammer will
Hits the
first.
ground first. Why?
Is it because there's
Heavier.
less-
Mass.
Cut.
Bigger
Oh.
mass.
No,
No?
no.
Because
Because the hammer falls straight down.
feathers.
What does the feather do?
Side to side.
The feather floats around and does this kind of thing, and then finally hits the ground.
Because of the air resistance.
Because of air resistance, that's right. So what about on the moon? You drop the hammer and the feather at the same time. Now there's no air.
Same.
Yep, they both fall.
Well, that's what
Straight
yeah,
down.
it was like in a
I know.
chamber with zero air.
Yes,
They'd hit
yeah.
the same.
They both hit at the same time on the moon. And if you put both in a vacuum chamber on Earth and then release them both somehow, you rig up some apparatus and you release them both at the same time on Earth in the vacuum chamber, they will both hit at the same time. You can probably look it up on YouTube. There's videos, people have done this, and it is true. They will both hit at the same time. Why?
Because there's no wind or air.
Okay, the air resistance is gone, but how come hammer, which is clearly heavier than a feather, how come they both will hit at the same time?
Because everything falls the same rate.
How come? How come everything falls the same rate?
Because of gravity.
Because of gravity.
Because
It
gravity.
does not matter. It does not depend on mass of the object.
It will
Gravity
always
pulls
fall
on
the same.
everything at the same rate. That's right. So that's why. And so that's why we're talking about free fall. Objects in free fall, regardless of their mass, have the same acceleration, which means they will all accelerate at the same rate. So if you drop two objects at the same time from the same height, regardless of their mass, they will hit the ground at the same time. It's not going to do me any good on the video, but if I were to take something very heavy and something kind of light, a ping pong ball and a steel ball, and I drop them, they will both hit my foot at the same time. Okay? It's just that one will hurt more. On the Earth, air resistance is a factor, though. But when you drop a heavy object like a hammer, air resistance can be ignored. So this is key. A heavy object, we can ignore air resistance. So this is something that we'll be dealing with a lot in this class. How can we simplify a problem like this, where we can ignore air resistance, external factors,
It's
where we can do that?
weight
So we can only make only a slight error in treating the hammer as if it was in free fall, and ignore the air resistance and simplify the problem for ourselves. Okay, so we do that a lot in this class. Motion with air resistance comes on later in this class. We'll deal with drag and stuff like that too. But for us in the beginning, it's not a big deal. Assuming objects in free fall are truly in free fall without air resistance. It's not a problem. We'll just say ignore air resistance or something like that. Okay? No big deal. All right, so the motion of an object in free fall. If we look at A, letter A, the object dropped from rest is speeding up, so its acceleration and its downward velocity point in the same direction. So we have the acceleration here pulling us down back toward the surface of the Earth. The acceleration and the velocity are pointing in the same direction. Therefore, we are speeding up. We can see the velocity vectors getting longer and longer as we go. In B, the graph has a constant slope. Therefore, free fall acceleration is constant. And right here, we finally see for the first time acceleration due to gravity is a sub y, because we're in the y direction, is negative 9.8 meters per second squared. Why is it negative?
Down.
Because it's down, and our standard coordinate system, positive x, positive y, says that up is positive. So therefore, acceleration due to gravity is negative. However, the 9.8 is actually a positive net value. But when we define our coordinate system as up, then it becomes negative, okay? This is a vector. Now, the graph for the velocity is a linear situation. Velocity is growing linearly. An object, so for C now, that object is initially moving up, is slowing down, so its acceleration and its upward velocity point in opposite directions. So if we throw an object up, right, acceleration due to gravity is always down. So that means that our velocity vector is opposite the acceleration vector, which means we'll slow down, okay? Now what happens once the velocity up here reaches 0? What does the object do? Just sit there?
No, it starts to descend.
It starts to come back down. Yeah, that's right. Okay. So we got to remember that. Now, despite the name, free fall does not mean the object is literally falling. It can be going up, as we saw up here in C. We're going up in this case. Okay? We're not falling, but it is still in free fall. Okay? It is a free fall problem. So, an object moving under the influence of gravity only and no other forces is in a state of free fall. Okay? This includes object falling straight down, objects tossed, so we throw a ball, that's a free fall problem. We throw something straight up, we shoot something straight up. Objects in projectile motion, so like the basketball, the baseball, those types of problems. Those are all free fall. Satellites in orbit, that's free fall also. Okay? Anything in orbit is free fall. And we'll talk about that later. The value for free fall acceleration varies slightly at different places on the Earth depending on your elevation. But in general, free fall is 9.8 meters per second vertically downward. Now because I said vertically downward right here, this is a positive 9.8 meters per second squared. But in a problem, if we define up as positive, then it would be negative 9.8 meters per second squared. If up is positive. Okay? You got to keep those things straight. Good? Okay, so now the magnitude of free fall acceleration has the special symbol g. So if you are using the symbol g, then acceleration is 9.8 meters per second squared. If you're using a, then a is negative 9.8 meters per second squared if you defined up as positive. Okay? G is 9.8. A is negative 9.8. So several points about free fall need to be made. G is a magnitude, and therefore it is positive. So if you see the letter G, it is 9.8. A falling object has increasing velocity and a negative acceleration. G is not the object's acceleration. G is a magnitude. The one-dimensional acceleration is a sub y equals negative g. So again, I just keep saying that because it's important. It's easy to confuse. Because free fall is motion with a constant acceleration, the kinematic equations for constant accelerations apply. So that means all of our equations that we've been using with acceleration in them, the one-dimensional motion problems, we can turn any x's into y and use those same equations. Okay? And then the acceleration is automatically the gravitational acceleration, so negative g. Once an object is acted upon by only the force of gravity, it is in free fall. A sub y equals negative 9.8 meters per second squared automatically. It doesn't matter how the object entered free fall. Once it is in the air, like a football that was punted straight up has the same acceleration of negative g as a rock that was dropped off a bridge. It doesn't make any difference what the object is. It is automatically that acceleration. G is not called gravity. Gravity is a force, not an acceleration. G is the free fall acceleration. So hopefully as I've been talking, I've not made that accidental slip. It's very easy to call that the wrong thing. I've been trying to say acceleration due to gravity. G is free fall acceleration. Okay? Acceleration due to gravity. All right, G is 9.8 meters per second squared, only on Earth. And really only at sea level. As we get higher up, G starts to change. As we get farther away from the surface of the Earth, to the point where if we get up into orbit, it is significantly less than 9.8. Out on the moon, it's totally different. On a different planet, it's going to be completely different, okay? You cannot assume it is 9.8 meters per second squared everywhere. If it's going to be different, you'll be told. But for the most part, on the surface of the Earth, it's going to be 9.8 meters per second squared, unless we're doing a very specific problem. Other planets have different values of g. All right, so we can also compute the acceleration of objects not in free fall in units of g. And so you'll be doing some problems where it'll say, like, what factor of g is this, or something like that, okay? So an acceleration of 9.8 meters per second squared means an acceleration of 1g, an acceleration of 19.6 meters per second squared, so that is double 9.8, that's 2g, and so on. You hear about like fighter pilots or something like that saying, oh, I was pulling 3 Gs or something as I was doing that turn. Okay, that would be 3 times the normal acceleration due to gravity. Okay. Sometimes when you go like through a sharp, like the bottom of a steep hill or something like that, you feel like a huge like pressure on your body. That's more acceleration due to gravity than you're used to. So stuff like that. Generally, acceleration in terms of g or g's is this: the acceleration that you are going through on top divided by 9.8 meters per second squared, and whatever that number is that you get is the g's that you are feeling. Okay?
Oh, so that's like, oh, okay.
So very, very easy to calculate. You just got to calculate your acceleration first and then divide by 9.8, and you'll have the g's. Got it? Okay, so just cruising along here. A heavy rock is dropped from rest at the top of a cliff and falls 100 meters before hitting the ground. How long does the rock take to fall to the ground, and what is its velocity when it hits? So, a super straightforward problem here. Very standard free fall problem. What do we do?
Find out what we have.
What do we know?
From
This
where
is-
the rock
It goes from 0.
Delta X.
Oh, so it's not going to be x.
Oh, that's,
It's going to be y, right?
Yeah.
Okay, so we do know delta y. What is it? Okay.
Yeah, no, sorry.
It's just 100 meters. And then what else do we know?
the G,
So we know a sub y
A
then.
sub Y, my bad.
A sub y is what?
Equals negative 9.8 meters.
Negative 9.8 meters per second squared. And what else do we know?
The initial T, initial Y. Which is
Okay, so time initial is
0.
0 seconds. And what else do we know?
Y initial. Wait, we already have delta.
We have delta y already.
Isn't it?
It is dropped from rest. What does that mean?
Oh, that means zero velocity.
Okay, so V initial is 0 meters per second. And all of this occurred at the top of the cliff up here. That's the rock, and it's dropping down. And then down here at the bottom, when it hits, what do we need to find out?
The final velocity is 0.
V final, we don't know. And time final, we also don't know. The final velocity is not 0.
Wait, it isn't,
No.
but it hits the ground.
Yes, it hits the ground.
But once it's
When it
velocity
hits the
right-
ground, it's not going 0,
Okay, yeah.
Oh,
right? If it was going 0, it didn't move at all. It's moving when it hits the ground. Okay, that's what we want to find out. Okay, so I put time final on there also because we might need to calculate that in order to calculate the final velocity. So that's something we don't know, but we might need it. Okay, so we have kinematic equations. We know delta y. We know the acceleration. We don't know final time. We don't know final velocity. We need final velocity. We know initial velocity. Is there a formula that deals with maybe a delta v or a final velocity, initial velocity, acceleration, and a delta y? Can we calculate all of this can we calculate final velocity without needing time? Is there a formula that does this?
Yes,
What?
I think, velocity final squared equals velocity initial plus 2 times.
Velocity initial, that's it?
Yeah, plus 2 times acceleration times delta x.
Okay, this is velocity initial squared.
Oh, is it?
Yep, plus 2a
I'll write that down.
delta y. It has to be squared because velocity final was squared. So this term has to also be squared to make the units agree. Okay, yeah, this formula looks good. We have initial velocity, we have acceleration, and we have delta y. So the only thing we need is velocity final, right?
Yeah,
All right, so what do we know in this equation?
but velocity initial
Initial velocity is 0, so that term is gone.
and acceleration.
And we know acceleration, we know delta y. So before I do anything, I'm going to square root both sides. And I have velocity final equals square root 2 acceleration delta y. And I can plug stuff in. Square root 2 times acceleration, negative 9.8 meters per second squared, times, okay, now delta y. How do you calculate delta y?
Distance from the beginning to the end.
YF minus YI.
Okay, so YF was what?
100. Or I 0.
This is Y final. That would be 0. If this was Y initial,
It'd be 100.
that would be
So it'd be
100.
a
So,
negative 100.
yeah, Y final minus Y initial would be 0 minus 100. This is actually negative 100 meters here. So when I plug this in here, this is negative 100 meters. And now negative times negative is positive, and that's how we wind up with a positive thing that we were square rooting to wind up with not an imaginary number, okay? Don't fudge your numbers. You look at that square root and you think, oh man, that's gonna be a negative thing. I must not need that negative sign. Don't do that. The math has to work, okay? So now we get what?
$44.2719.
What? Oh, I didn't square root, that's why.
2719.
Yeah.
Okay, but that's not gonna be our answer. What is our actual answer gonna be?
For significant figure, what would it be 44.3?
How many significant figures do you think we have?
Well, because we have the negative 9.8.
9.8 is a known number. We're not gonna count that.
Would it be 3 then? So,
You're gonna call it 3?
yeah,
So 44.3
yeah,
meters. Is that right?
seconds,
Seconds?
yeah.
Yeah, there's seconds.
What are we calculating?
Meters per second.
Velocity
Oh,
final.
yeah, so it's just, yeah.
Look at the units in the square root. Meters per second squared times meters gives
So
us
it's-
meters
so it's
squared
just-
per second squared. I square root both and I wind up with meters per second. We're calculating velocity. We better wind up with meters per second. So that's how fast it's going when it hits the ground. 44.3 meters per second. Basically, half your football field per second.
That's quick.
It's pretty fast. Anything else we gotta calculate? How long does the rock take to fall to the ground? Did we need to calculate the delta t? Time final? Yeah, we do. Okay, so I need a formula now for that.
Do you even understand what he said? I just
Time final.
Yeah, I speak yawn.
What about delta t? Is that fine?
So we need delta t, yeah, basically.
Okay. Velocity final equals velocity initial plus acceleration delta t. And then just flip everything to the other side and find the delta t.
Think so?
I Okay.
What if we made a mistake on our velocity final?
Oh, then everything.
Then we'll have a wrong answer on this too. How about this one? Y final equals Y initial, which we know, plus V sub I delta t plus 1/2 acceleration delta t squared. What do you think about that? What's 0 on this one?
Velocity initial.
Velocity initial was 0. What else?
Y final.
Y final was 0. And so we just have Y initial and 1/2 A delta t squared. That's pretty easy.
So 100. We'll substitute now.
No, solve for delta t.
Okay.
So move the Y initial over, negative Y initial. Multiply both sides by 2 to get rid of the 1/2. So put a 2 there. And then divide both sides by A. Divide by A. And then square root. And I have delta t. You follow that? No?
Divide the A. Multiply by 2. Do you not multiply the bottom by 2?
I'd multiply both sides by 2 to get rid of this 1/2.
Yeah, but would you not have 2?
But
acceleration?
he did the 2 first,
Oh.
so you don't.
You won't do that. That's a-
Okay, so then plug stuff in. Square root, negative 2. Y initial was 100. Divide by acceleration, which is negative 9.8. Oh, this is meters here. Meters per second squared. The negatives are gone, which means we have a positive result, which is good. This would be 200 on top, 9.8 is basically 10, I'm just estimating. 200 divided by 10 is pretty much 20. Square root of pretty much 20 is going to be somewhere between 4 and 5 seconds.
4.51754.
There you go. So 4.5 what?
17.
So 4.52
Yeah.
seconds. We kept 3 before, we might as well keep 3 now, right? 4.52 seconds is how long it takes to hit the ground. Does it matter that it was a rock? No. What if it was a bowling ball?
Kind of same thing, but
Same result. What if it was a penguin?
penguin.
Yeah,
It does after it hits.
same result. What if it was a loogie?
Same result.
Same result. It doesn't matter what it is, right? As long as we can ignore air resistance, then it doesn't make any difference. As long as it was from rest when it started. Okay? All right, draw a motion diagram and a velocity versus time graph for a ball tossed straight up in the air from the point that it leaves the hand until just before it is caught. So the motion diagram is these dots. We leave the hand and we throw it straight up, and we're going to give it a lot of velocity right away so it can go up in the air. So this is going to be V. We got to label that. A lot of velocity right away. And then what happens to the velocity right away?
It starts slowing down.
It starts slowing down right away. So we got to show a shorter vector, shorter vector, shorter, and then finally, basically, it comes to a stop.
So it'd be like this?
No. So that's what that looks like. Now, it's not just going to stop there because it says ball is tossed straight up in the air from the point that it leaves the hand until just before it is caught. So it comes back down. So we can make a second one off to the side over here. And now it's coming down. So it comes down quickly or slowly?
Slowly.
Slowly at first, and then it starts speeding up. So here we are, and then a little bit faster, a little bit faster, a little bit faster, faster, and then finally when it comes back down, it's going basically the same speed as it was before. Now, one thing that you probably all missed, we label the velocity. Did you label the velocity? You gotta label the velocity But you also have to say one other thing. Which way is the acceleration going?
Oh,
Don't forget the acceleration vector. Okay, so that's our motion diagram. Now we got to draw a velocity versus time graph. So we can put our axes on there. Now we want to make sure we can show positive velocity and negative velocity. So here's our velocity, and that's going to be in meters per second. Velocity is a function of time in meters per second, and then this is going to be time, of course, and that's going to be in seconds. Now, we throw this ball up. So what is its velocity in the beginning?
9.8.
No.
No.
What is its velocity in
Positive.
the beginning? Positive velocity. A lot of velocity or a little velocity?
Lots.
A lot of velocity. And what does the velocity do as it goes up?
Gets smaller.
It gets smaller and eventually it becomes what?
Negative.
It becomes 0, right? Okay, so it starts up here and eventually becomes 0 as time goes on. Now, what happens next? The velocity becomes negative, a lot or a little,
A lot.
in the beginning. When it's up
Oh, wait, no,
here,
it's slow.
it's slow, and then it starts to grow, right? Does the velocity grow and become negative big? Yeah. So remember in the beginning, I told you velocity, because of a constant acceleration, is linear. This was a constant acceleration. So therefore, the velocity versus time graph is going to be linear. It looks like that. Okay? And by the way, neglecting air resistance, these dots here, these vectors, should be
The same.
the same. So this correlation here, this dot right here, whatever that is, should correspond to that dot right there, whatever it is. Okay? So if we threw it up at like 30 meters per second, it should come down at 30 meters per second, right? What goes up comes down, neglecting air resistance at the same speed. All right? Shoot a bullet up in the air, it's going to come down at the same speed, in the same spot. So get out of the way. Don't shoot bullets up in the air. It's a dumb idea. All right, a springbok is an antelope found in southern Africa and gets its name from their remarkable jumping ability. I've actually seen these do that, do what we're about to talk about here. When a springbok is startled, it will leap straight up into the air, which is a maneuver called a pronk. I spent some time photographing pronking. This is what they do as a defensive maneuver to evade their predators when they're being attacked. They'll jump straight up in the air. They also do it to impress the ladies, like the springbok males that can jump up higher, kind of are trying to impress the females, like it's a mating ritual. Anyway, a particular springbok goes into a crouch to perform a pronk. It then extends its legs forcefully, accelerating at 35 meters per second squared for 0.7 meters as its legs straighten. Legs fully extended, it leaves the ground and rises into the air. At what speed does the springbok leave the ground, and how high does it go? Okay, so these are like little antelopes. Picture smaller versions of the pronghorns that we have around here. Okay, and they're just jumping straight up. They're just standing there. They crouch down a little bit, and then they just boing up. Okay, that's what a pronk is. So we're going to try to solve this problem. It is kind of a complicated problem. It's going to be solved in like 2 phases. So at what speed does the springbok leave the ground, and then how high does it go? Once it left the ground, this is in free fall here. Prior to that, this is a launch here in part A. Okay, it's just launching itself off the ground with an acceleration that it is giving itself. And we'll calculate that acceleration right there. Okay? All right, so first, What do we know?
Velocity initial.
So like two phases to this problem. In part A, we know the acceleration in the y direction is here, 35 meters per second squared. What else do we know? As it's crouched down and it starts to launch itself, what else do we know in this phase?
X initial or Y initial.
See this amazing drawing right here?
Yeah.
Okay, so this is like phase one right here. Okay, what do we know in phase one? You said y initial is what?
0.
Okay, what's y final?
You don't know,
Yes, we do.
do we? And rises into the air.
0.7.
Yep, 0.7 meters. Okay? Now what? What else do we know?
The
Time initial.
Time initial is 0.
Okay, so we don't know anything about time final, so I'm just going to put delta t. We don't know that. What else do we know or don't know?
You don't know the velocity final. So delta V.
Okay, so vi equals 0 meters per second. V final, we don't know.
And that's it. No?
That's it?
Yes, that's it.
Okay, so we need to calculate velocity final for this situation so that we know how fast it's going for the free fall portion of this problem. Okay? At what speed does the springbok leave the ground? That's what we need. So I need some sort of formula for this.
Oh, we have delta Y as well, which is 0.
We have delta y, yes.
Velocity final squared
Okay.
equals velocity initial squared.
Velocity final squared equals velocity initial squared plus
2 acceleration times delta Y.
good. And what is delta y? Vf or yf minus yi, right? So what is it?
0.7.
It is actually 0.70 meters. Yeah. Do we know everything in this equation?
No.
Is anything
Not
0?
Velocity final.
Initial velocity is 0. Acceleration we know. Delta y we know. We're just looking for velocity final, so we can solve this one. Square root both sides. Velocity final equals square root 2ay delta y. Plug in your numbers. $70 times 0.7 would be 4.9,
Yeah, I got 7.
yeah. 7 what?
Just
Yeah,
7
meters
so
per
it's
second.
Meters
Oh.
per second. And this is 7.0, right?
Mhm.
Okay. So we have 7 meters per second. This was actually part A. So 7 meters per second is how fast the springbok leaves the ground. Now, at this point, it doesn't matter what the object is. It's a living animal, it's a rock, it's a baseball, it doesn't make any difference, right? Okay. So now part B, how high does the springbok go? What do we do?
How high?
Yeah.
So we want delta.
Now we're looking for a delta y, a
Oh,
y
yeah.
sub f, right? What do we know for this part of the problem?
Y sub I.
We know y sub I
which is 0.7.
is, nope,
No, just 0.
it's 0. As its legs straightened, the body of this animal went up 0.7 meters, right? The body of the animal went up 0.7 meters. So, what do we do?
We would find what the initial velocity is, right? And then subtract it from 9.8 meters a second squared.
We just need an equation.
Oh, we want to find the y sub I?
Yeah. We want to find y, or delta y.
Y sub f equals sub I plus vi delta t.
We can actually use the exact same equation that we just used.
That one?
Yep, v sub f squared equals v sub I squared plus 2 ay delta y. What is going to happen when we get to the top of this spring box jump?
It's the peak of your,
The peak of the jump. What's going to be true?
It's going to be
your delta y and your delta f,
Delta y is what we're looking for.
your final velocity.
What about the final velocity?
0.
It'll be 0. So this guy this time is gone. Velocity initial, do we know that?
In this scenario, it'll be
7 meters a second.
It'll be the 7 meters per second that we just calculated. What about the acceleration? Do we know that?
it'll be negative.
Negative 9.8.
Negative 9.8, because now this is a free fall situation, okay? Different acceleration, it's free fall. And then the delta y is the thing that we don't know, right? So we can now solve this equation for
Delta y.
delta y. Good.
So
Okay.
You moved it over, so it's negative delta y,
Now I'm going to leave the delta y right where it is.
and you move everything else.
I'm going to move everything else. So I'm subtracting v sub I squared,
Negative v sub I squared.
and then what?
Divide by 2.
Divide by 2a sub y. And I get delta y by itself. All right. So now a negative, and then what is v sub I?
7 meters a second.
7
Squared.
meters per second, and that's being squared. Divide by 2, what's a sub y?
35 meters a second.
What is it?
The 9.8, negative 9.8.
Negative 9.8 meters per second squared. Okay. Now, I square 7, and I get 49, but it's negative, so it's actually negative 49 meters per second squared. You understand that, right? Okay. And then on the bottom, 2 times negative 9.8. So the negative on the outside and the negative on the bottom are going to become positive. So we'll get a positive answer.
I want to see if you guys. Oh. I don't think I did that right.
Yeah, 2.5.
2.5. What?
No.
Meters. Wait.
So meters per second got squared. So this is meters squared per second squared. And on the bottom we have meters per second squared.
Oh.
So meters squared on top divides out with one of the meters, and we're left with meters per second squared divided by per second squared. The seconds squareds are both gone. We're left with just meters. 2.5 meters. What part of the animal went up 2.5 meters?
The entire body.
The
So
legs.
what's the lowest part of the body?
The legs.
The hoof. That's the part that went up 2.5 meters. The rest of it is even higher than that, because the delta y went from the ground. Okay? 2.5 meters is how high?
7 and change.
Well, yeah, like almost 8 feet.
Yeah.
So the rest of it is even higher than
It's got
that.
some hops.
It does.
Holy,
Yeah.
that's
So, like I said, I've actually seen this happen. We spent some time trying to photograph these animals doing that, and they weren't being chased by anything. They were just, it was mating behavior. They were trying to impress, And so the males were pronking for the females, and it was amazing. Yeah,
That's really high.
yeah, it's high.
I think
We should see some
I
pictures.
think our dog might be part.
Park Springbok.
Because like at our old house, we had 7-foot ceilings, and he'd get so excited he'd start bouncing,
Yeah.
and he'd launch himself and he'd hit his head off our roof.
Oh wow, that's pretty good.
No
Yeah,
wonder-
maybe in a past life, Park
No
Springbok.
wonder he's a little retarded.
All right, so a volcano ejects a chunk of rock straight up at a velocity of 30 meters per second. Ignoring air resistance, what will be the velocity of the rock when it falls back into the volcano's crater?
Negative 30 meters per second. D.
You guys agree?
Wait, why is there less than symbols?
Greater than 30 meters per second, 30 meters per second, 0 meters per second, negative 30 meters per second, or less than 30 meters per second. Those are the only options, right? We've covered the entire spectrum.
It should be negative 30, right?
Wait. I'm thinking E now. Wait, because I'm thinking negative 9. Wait. Negative 9.7 times. And above. D.
Yeah, D.
Yeah, it's D.
Yeah, okay.
Why? Tell me why.
Because we were going up, now we're going down.
Yeah.
We were going up, that's positive.
If it
Now
goes
we're,
up at 30, then it'll come
yep,
down.
now we're coming back down. What goes up comes down, right? We're talking velocity. So the sign matters here.
But won't it speed up?
No. Well, it speeds up as it comes back down. Ignoring air resistance, it's going to come back down at exactly the same velocity as it went up. So if it left at 30 up, it's going to come back down and hit at 30, exactly.
Unless if you remove that surface.
If we're talking about air resistance, then it's going to be different, but we're not. So there you go. Okay?
Like what I was talking